Let me screen share and then bring that up. Cool, screen share. All right, cool. So yeah, you should see this at that link, and then you scroll down to week 5 and click slideshow, and you'll see these slides, if all worked well. And so, yeah, we can go through this. And great, the outline is just, I'll go over some questions from homework 1, and then I will spend the rest of the time going over pandas, because the general like rubric for what we did in lecture in the past week has just been like pandas, right? Like each of the lectures has had its own title and stuff, but really it's just pandas. But for homework 1, basically like we have been told that we can go over like a few of the questions, but then we do like need to hit all the pandas topics. So yeah, the 4 most missed questions, I went last night and I calculated like the most missed questions, because again, I can't go through all of them. And if you have individual questions that aren't one of these, like we'll have to do it in office hours or Piazza or something, or email. But these are the 4 most missed questions, right? And it kind of works out because one of them is question 5B, and then the rest are just all question 7. So let me just go through those. Question 5B, yeah. I wish that maybe I could get feedback from you. I don't really know. The question 7 was like, I get why it was difficult. I don't really understand this one, but I'm not trying to be like I'm not trying to be like mean about it. I don't mean that like, oh, I don't know what's wrong with it. I just literally mean like, I don't know what the sort of, what people got tripped up on. But yeah, sorry. So question 5B is like, what is it about selecting on the dependent variable that limits our ability to draw inferences about the causal relationship between independent variable and outcome, right? And the thing is that all of the ones except C just had nothing to do with selecting on the dependent variable whatsoever. So that's how I would have gotten this question, is I would have just been like, so what I wrote here, right, which is like A and B are just problems that happen with studies in general. They're not related to like, they're not specifically related to selecting on the dependent variable, meaning like whether or not you select on the dependent variable, you're gonna run into these. These are problems that you can run into, right? So C, then I would read C and I'd be like, okay, so we do not observe whether the factors. Yeah, this C is the one that is the issue with selecting on the dependent variable. When I think about selecting on the dependent variable, I think about like selecting. Yeah, so I think about the example of like, I forget whether we talked about it in this class or not, but in previous instances of the course, we've talked about this article that was like, we studied the properties of mass shooters to find out why they mass shoot. And it's like, that doesn't tell you anything, because, for example, you could just be like, wow, guys, we figured it out. We figured out why people do mass shootings. We looked at all the mass shooters, and it turns out that 6 out of 7 of them are right-handed. So if you meet someone that's right-handed, be careful, because that's probably a mass shooter, right? But the point is like, no, that's not how statistical inference works, right? Because the point is that most people are right-handed in the world, right? So it's like, if all people are mostly right-handed, right, it's 6 out of every 7. Specifically, mass shooters are gonna mostly be right-handed just because they're like pulled from the population, right? That doesn't differentiate mass shooters from anyone else in the population. And yet, if you select on the dependent variable, you'll just be like, wow, wow, look at how high a percent of these mass shooters are right-handed, right? And you'll just find that with anything. Like, it doesn't tell you, you're literally unable to draw any conclusions whatsoever about what particularly makes someone decide to become a mass shooter versus deciding not to become a mass shooter, right? If you want to have both of those, you need the comparison. Cool. So that's why like C, like I would like rating them in order, it'd be like A and B are general issues. C is the issue, right? Like we need to be able to compare top performers with not top performers. And then D is just like the weirdest one because it's just false. Like there's nothing, we have to be more careful when drawing causal conclusions from observational data versus experimental data because we don't have all the nice, features of an experiment like built in. But it doesn't mean like, oh, we must never draw causal conclusions, right? And just to drive this point home, and also out of shameless self-promotion, here's like a link to a project that I was a research assistant on, right? Called like, it's like Democracy Does Cause Growth, right? And these are like, this is my advisor at Columbia. But I'm just showing it to you because it's like an example of like, it's in the Journal of Political Economy, which is like one of the top journals, right? In what I do. And then, so like it got accepted even though it is drawing causal conclusions, right? Cause is right there in the title. So it's drawing causal conclusions even though it's fully observational, right? And that's because any analysis of like historical data is going to be observational, right? Because we can't do experiments with history. We can't be like, in this case, we can't be like, all right, we're going to take all the countries in the world and we're going to randomly assign them so that this half are democracies and this half are not democracies. And then we're going to wait 50 years and then we're going to measure their economic growth, right? You can't do that. I mean, you can try, but it's going to be difficult. But for this, right, that's not what they did. They just took the observational data, and then the point is like each thing in it is like addressing a bias that comes from the fact that it is observational data rather than experimental, right? So for example, in the abstract, it's like we do a dynamic panel strategy, which controls for country fixed effects and the dynamics of GDP, which otherwise confound the effect of democracy, blah, blah, blah. We introduce a new indicator that consolidates, et cetera, et cetera, et cetera. This is all stuff like from the class that you'll recognize, right? Confounders, right? Confound effect of democracy, measurement error. So I just wanted to bring that up because it's like, no, you definitely can draw causal conclusions from observation. You can't, it's different, right? From proving things. This isn't proving democracy causes growth. It's saying that like we draw the conclusion that from this like data set that like our degree of belief that democracy causes growth is like high enough to publish it in a journal, right? If it helps, or if it hopefully doesn't make it more confusing, like Bayesian statistics, like kind of like modern statistics, is all about degrees of belief, right? It's never like true, false. It's always like, what is my degree of belief in this hypothesis? So that's what it means. That's why, like, in case you get confused, where it's like, we must never say that we've proved causality from observational data. That's true, but that's also true from experimental data, right? We should never say we proved causality ever, no matter what, because we can't. But in like Bayesian statistics world, like modern statistics world, like the point is that we draw conclusions based on the degree of belief in this hypothesis over another hypothesis. For example, that democracy like doesn't cause growth or whatever. Right. So I just wanted to include that because it's another like real world example on that. So for question 7, I have an idea, which is that my laptop's going to run out of batteries, and then maybe we'll do like a 30-minute water break, and then we'll run over to the cafe over there. And they do have plugs that work because I work there a lot. Cool, problem solved. And you get a break. But there'll be a split, right? Because after, yeah, we'll do the homework 1 questions, and then we'll do Pandas stuff, Pandas material. So question 7, like I do understand why it was tricky because you just suddenly had all this nomenclature, all these buzzwords and stuff like thrown at you, right? Like independent variable, dependent variable, confounder, causality, and then you had these like diagrams thrown at you as well. But for question 7, all of the questions were just asking like, what's a potential confounder? And then it provided options. And so I'm going to show you like a process by which you can just answer those types of questions if they come up on an exam. But the point is like, yeah, I don't know how long to spend on it, but like different schools will like train statisticians in different ways. Um, and I'll just say like if you if you study at like Stanford's computer science department, right, which is my like background, like they will always draw these little diagrams that you have here, right? They call them like probabilistic graphical models. In this class, we just call them causal diagrams or whatever. We don't like, we're not picky about the name of them, but these diagrams where like each of the nodes, each of the little boxes is a variable, and then the arrows imply like potential causal relationships, right? Or like posited causal relationships. So I just wanted to explain that because like, that's why like in my brain, I just can't, I have to draw these diagrams. I can't really like reason through these types of problems very well without drawing it, right? To the point that like, yeah, my advisor didn't get trained in these causal diagrams, so we're constantly on like whiteboards like translating um, between like his like method of writing it and mine, which is like these diagrams. So uh, you might read a statistics textbook or something that doesn't use these at all, but I need to use them when I think about confounders, right? Because a confounder is the thing in this diagram here, which is like you have your theory right at the top, which is x, the independent variable, has a causal impact effect on y, the dependent variable, and then a confounder is by definition, like the definition of a confounder is a variable that has a causal impact on both the independent and the dependent variable in your theory, right? So if there's some variable z that has a causal impact on x and y, that will bias the results if you don't include it, right? If you don't consider it. So that's why we care about confounders. Um, my laptop's already on red, so what if we take that, like I can literally see it from here. I can see the electrical plugs from here. So uh, let's take a 3-minute water break and then I'll be right back. And we'll do these confounders because you'll see, like I just do these diagrams and I'll walk through like, you're just plugging in the options into this confounder box, right? And seeing the diagram makes sense. And the diagram that makes the most sense, that's the most parsimonious, is the answer. So BRB. Sorry about this. I thought the plugs would work. Okay, one second. right, that wasn't that bad, right? Hopefully. Cool, and it's being recorded and everything. All right, great. So let's go back to the slides. Cool. All right, so I mentioned these diagrams, right? These causal diagrams. And, you know, they have a million different names, but the process that I was talking about for like figuring out questions like this is that you say, okay, step one is like you identify the theory in the first place, right? So what is the like hypothesis that's being posited that might have a confounder that makes the hypothesis invalid, right? Because in this case, it's saying, okay, on average, people who join the Marine Corps are less likely than those who don't to be diagnosed with cervical cancer, right? So we want to identify like two variables in that, and then what it is positing is the relationship between them, right? In this case, join the Marine Corps, right? That's one of the variables that it is positing a relationship about, and the other one is being diagnosed with cervical cancer, right? This one. So the sentence, right? It's thankfully it just says like independent and then dependent variable in order, right? Meaning left to right in the same way as the diagram, right? So that's what you do first, right? You just identify like what's the theory. Cover up this biological sex part for a second, and just look at like what is it is positing that there is a causal relationship, or it's hypothesizing that there's a causal relationship between joining the Marine Corps and being diagnosed with cervical cancer, right? But then the question is, before we recommend joining up as a preventative treatment, what's a likely confounder? So then, given like our definition of confounder from this slide, we just think like, okay, so we have identified our independent variable and we plugged it in there. We've identified our dependent variable, plugged it in there, and now we want to take these choices and we want to see like, would they make sense? Would there actually be a causal effect going from the confounder to both the independent and the dependent variable, right? In other words, we're making like stories, right? For each of these, you plug it in the like confounder slot in the diagram, and then you're thinking like, is there a feasible, right? Is there a feasible story of how this particular variable could affect both the independent and dependent variable in my theory? Because if it can, then it's going to mess up our results, right? And then I think the reason a lot of people got this wrong, or got parts of this wrong, is because it's tricky because we haven't learned like the names for when there's just a missing variable that affects only the independent variable, and then when there's a missing variable that affects only the dependent variable, right? So there's like three different types of omitted variables that could happen, right? First could be an omitted variable that only has a causal impact on the independent variable. And there's an omitted variable that only has a causal impact on the dependent variable, right? But a confounder is a third thing, very specifically, where it is only a confounder if it affects both, right? So I think a lot of people just were like, oh, I see the relationship between, for example, military healthcare plan and being diagnosed with cervical cancer, right? That story is like easy to, that's a parsimonious story. Because you could just say, oh, well, if you have the military healthcare plan, then it's like, hey, now you can afford to get a screening for cervical cancer, right? So you might like just put that answer because you say, oh, okay, I see how having military healthcare plan would have a causal impact on being diagnosed with cervical cancer, right? But the problem there is that confounders have to affect both the independent and the dependent. So now you've told the story of how it affects the dependent variable, but not the independent variable, right? Because the story doesn't make sense. There's no sensible story for how being on the military healthcare plan would cause someone to join the Marine Corps, right? Because that's reverse. Like, if you remember Prof. Sperling's lectures, he talked about how one of the conditions that needs to hold for causality is like if X causes Y, X has to temporally precede Y, right? So in this case, like this would be violated because you would be saying that getting the military healthcare plan causes someone to join the Marine Corps, right? But it's the other way around. It's that when you join the Marine Corps, you get the military healthcare plan, right? So the story doesn't make sense for a military healthcare plan affecting the independent variable. The independent variable affects military healthcare plan, but then that would be the arrow flipped the other way, right? So it's not a confounder. Whereas for biological sex, throwing away all the complexities of what that even means, versus like gender, for example, biological sex, in quotes, like affects joining the Marine Corps because, I mean, back in the day, like you wouldn't be able to join the Marine Corps. I don't know. I don't actually like know a lot of the stuff, the military, but I don't know if you can join the Marine Corps as a woman, but you definitely couldn't in the past. And so it would affect joining the Marine Corps, and it would affect being diagnosed with cervical cancer as well, right? Because of, it's like if you have a cervix or not, right? That affects whether you can have a cervical cancer, whether you can have cervical cancer. Cool, so that's why C is the answer for that. And then we just repeat that, right, for part B and part C. Sorry, that's why C is the answer to A, and then for part B, we draw the same diagram, right? And we start, I should have done it in like stages. I'm sorry about that, but for now, just cover up the US citizen part here, right? Because we're just trying to fill in the X and the Y first, right? We read the sentence and it says, on average, people who can vote in New York City are more likely to support the US team in the World Cup than people who can't, right? And so we read that and we say, what are the two variables where the relationship is being positive between them? One is definitely people who can't vote, people who can vote in New York City, right? And then the more likely to support, that is like that's describing the arrow in the diagram, not the nodes, right? So we'll get back to that, but this right here is describing a node, right? Like a little box in the diagram. People who can vote in New York City is one variable, and then support the US team in the World Cup, right? That's another. And so once again, it's listed in the order of independent and then dependent variable, which is nice. So we make the top part of our diagram immediately from that sentence, right? Eligible to vote in New York City, and then an arrow about positive relationship, in this case, more likely, right? An increase in dependent variable supports US team in World Cup. So if we wanted, we could put like a plus sign there, but that would be like a more specified causal diagram. But now, for answering the question, it says, before we recommend sending out voting materials to improve support for the soccer team, what's a likely confounder? And that's where, right, we take out our diagram and we say, okay, the confounder is the thing that would causally affect, in other words, have arrows leading into the independent and the dependent variable, right? So in this one, there was this one is pretty tricky because there are some stories you could come up with of, like, for example, age, right? Like, say we put age in the confounder slot, you could say, well, yeah, age definitely affects eligibility to vote in New York City, right? Because you can't, if you're under 18, you can't vote. So that's a huge, like, there's a deterministic, like, if you're under 18, not eligible to vote. If you're over 18, you may be eligible to vote, right? So it definitely affects the independent variable, but you have to always remember that a confounder is the thing that affects independent and dependent, right? So in this case, does age affect supporting the US team in the World Cup? Yeah, in office hours, we did a lot of like discussions about this, and you could always come up with stories, right? Like, for example, young people are better at using the internet, and they can like find the games and they can like follow the players, right? They can like watch all the World Cup games and like be more involved in it than like older people who don't know how to find game streams on the internet or something. So you can come up with stories like that, right? But the point, like the exercise in this problem was to come up with the most parsimonious story, right? Like which is the most likely confounder has to do with like parsimony. And I keep saying that word. It's a weird thing. It's also sometimes called Occam's razor in like science. And it's just the idea that certain theories require less leaps of imagination or like leaps of argumentative logic than others. So it's just the classic, like, how do I put it? What's a good example? Yeah, so in this case, it's like, you could tell that like internet story in terms of why age affects support for the US team in the World Cup. But think about how many like argumentative steps that requires versus the alternative where you put US citizenship status in the confounder slot, right? Because now US citizenship status, the story become really straightforward. Because US citizenship status just is like pretty much 0-1. Like if you are not a US citizen, you definitely will not be eligible to vote in New York City. Whereas if you are a US citizen, you will be eligible. I mean, you'll have to like go to New York and establish residency, but it's like you're definitely not eligible to vote if you're not a citizen, right? So it's like a very to the point story. And then there's also a very like to the point parsimonious story for how it affects the dependent variable. In this case, just people who are citizens of a nation because of nationalism will tend to support the team of that nation in the World Cup, right? So if you're a US citizen, like if you meet someone and you don't know anything about them, right? You might say, I don't know what team they support, right? But if you learn they're a US citizen, suddenly you have information that lets you make inferences like, oh, I don't know that they support the US team, but they're more likely to support the US team, right? Than otherwise, like if they were like an Austrian citizen. So that is there's like a very straightforward arrow on how being a US citizen has a causal impact on the dependent variable as well, right? So the answer there, again, tricky because you come up with stories for almost all of these. In fact, we did in office hours come up with stories for all of these, but the one that was like the most parsimonious, required the least amount of argumentative leaps was US citizenship status. Same thing for C. Hopefully it becomes like routine for you almost. You read the sentence, you identify your independent and dependent variables. In this case, it's like people who eat dinner earlier in the day. So it's like time of eating dinner, right? And then tend to be more at risk from flu. So at risk from flu is the other one. And then again, more is kind of describing the arrow, not the nodes themselves. But so that's why it's like a connector in between the independent and dependent variables. So yeah, eat dinner early, and then an arrow of a posited or hypothesized causal relationship, and then risk of contracting flu, right? And again, before we suggest waiting until 11 p.m. to eat, ward off sickness, what is a likely confounder? We look at these options. Like if you didn't have the options, then you come up with it in your head, right? But in this case, we have these options, and we see like, do they make sense? Which ones do and do not make sense in this confounder slot in a causal diagram, right? So I'm trying to think of the stories that we did for this one in office hours. Oh yeah, region of country. So you might think you might try region of country first, and it'd be like, okay, region of country, eating dinner early. Yeah, there could be regions of the country that don't have electricity, right? Which means like they eat dinner early because they like to have like sunlight. I've lived in places in the world where like there are just parts that don't have any electricity, and then there are parts that do, even though they're the same like time zone. So then yeah, people who live without the electricity will eat dinner earlier. So you can causal arrow there, and then also you could come up with a causal arrow of region of country and risk of contracting flu, right? Because like there are just regions that have more mosquitoes, for example. So that one is like very tricky because region of country is like a pretty good answer, but age is like, but I didn't write this assignment, right? But the people who wrote it, they put age as the correct answer because age is like slightly even more parsimonious than those two stories. Because if you put age in, it's like, is the case, but it just like is the case that the older people eat dinner earlier, right? So that's the arrow from the age that's the causal arrow from the age variable to the dinner time variable, and then age to risk of contracting flu is just like has to do with like development of antibodies, you know, immune system, and how that relates with age. So I don't know. To me personally, it's somewhat of a toss-up between B and C, but C, if you like write it out, it's like slightly fewer leaps in most cases, right? I'm just saying that like this is the point of this is not that there's a correct answer. The point is more just to have you do the exercise of thinking through what the stories would be, right? So like if you write an answer for a question like this, say on like an exam or a midterm, you can also write like your stories like, oh, I think that the answer is region of country because region of country can have a causal impact on dinner time because of this, and then region of country can have a causal impact on flu susceptibility because of this, right? And like I'll read it. So like it's not like, oh, correct and incorrect. It's just shades of correctness in a way. And that has to do with the Bayesian stuff I talked about earlier, where it's like Bayesian statistics, it's not like there's true or false theories. There's just theories that that like a general person would have a higher degree of belief in than other theories. Putting them into details aside. Cool. So that's homework 1, right? And now Pandas. Oh, and like I said, if there are other homework 1 questions, I just like can't go over them because of the restrictions on what we can cover. But you can email me or go on Piazza or come to my office hours for sure. Cool. So Pandas is just like a Python library, and the way that I like to motivate it is that we look at it as a like the sort of like primary data type in NumPy is an array, right? Which is just like a one-dimensional list of numbers. And so NumPy gives us like a bunch of mathematical functions and stuff for working with these one-dimensional arrays. I mean, it also provides for two-dimensional, but the main, like the building block of NumPy is the array. It's a one-dimensional data structure, whereas like Pandas, sort of the building block of Pandas is the data frame, right? It's like that's the name data type, and it is a 2D table of data, right? So you can imagine like a bunch of 1D arrays stacked on each other, right? And so as data scientists, right, we're usually not just looking at like a single, we are looking at a collection of numbers, right? Meaning like we have data on a bunch of like people, for example, right? And for each person, we have a collection of data about them, right? And so that's why like Pandas makes a little more sense as data scientists. Like you're going to be using Pandas a lot more directly than NumPy, right? Like NumPy provides like these basic statistical tools, but Pandas is like, at least for me, like when I've worked as like a data scientist or research data analyst, is what I have Pandas open all the time, right? I'm thinking in terms of Pandas, right? So because of that data frame structure that it provides. And just the last thing before we dive into the like code, there's a whole set of like arguments about how data unquote should be structured. And you can like Google it and stuff, but for the sake of this class, like I don't even know if Jay or Sperling will like mention it explicitly, but basically like tidy, it's called tidy, T-I-D-Y data, and it's just like a philosophy of data management. If you have a data set, like each row should be a unit in your study, right? Like a unit in your theory. So if you're studying people, like if you're doing a medical trial, then a unit can be a person. So a row is a person. If you're studying, like if you're a macroeconomist and you're studying countries, then a row can be a country, right? It's just like whatever the unit of interest is. And then a column is a property of that unit, right? So in the case of a person, it could be like height, weight, age, for example. Whereas for a country, it could be like GDP, population, whatever, right? So that's kind of like the general format we want to think in. We use pandas. So now to get to the code, right? The way that these like data sets actually tend to work is you get these data files, right? And there's like a million formats, but CSV is kind of like the most standard one. Like let's say like it's the most optimal one for a lot of reasons, but mainly because CSV as a file type stands for comma separated. And the thing that's nice about it is that it contains the data in a format that the computer can read, right? But that's true of all the data formats, like an Excel file or a Stata file. But the nice thing about CSVs is that like if you're, say your program like Excel or Pandas or whatever isn't loading it correctly, you can open it as like a human, like it's like a human readable format, meaning you and I could just open it in like a text editor on our computer and see what's inside of it, right? We don't need like a separate program. Like we can load it into a separate program and we will, but if we want to get a preview of it, we can just open it and look at it in like a text editor. So in this case, I got really sick of using the horses data set because I don't know if I've ever like, someone asked me in another section if I don't know if I've like seen a horse in my life, like maybe. I'm just from like cities and we don't really have horse. I guess I've seen like a police horse, but anyway, I don't really know anything about horses, so it's just not my element. So I just dropped the horse data set thing and I put in this data set, which is like a data set where universities in the US are required to report to the federal a gift from a foreign entity, whether it is a private or public entity, like a government or a private company or individual. It has to be reported. So that's this data set, right? And it just comes, you just go on the website for like the federal, I can't remember what it is, I can find it. But you just like download it and it's this .csv file, right? So that's how a lot of data science works. You're not even ever having to worry about constructing your own data sets. You just get them in .csv format, right? But now, so we download it from the website, the government website, and we can just open it in a text editor. So let me like show you what that looks like. It's kind of annoying because I have to unscreen share from that, screen share on the text editor. And give it a second to load. Cool. And the CSV is like it's in your, it's on GitHub, right? It's just in the same folder as the notebook. All right. Well, now in every section I've gotten questions about whether I can cover questions from the homework. I can't because of the restrictions that were placed on TAs, that there's just a set of things that we are required to cover and we're not allowed to cover. I'm not like making that up. It's extremely dictatorial, and I can't like cover any questions other than the ones that I just covered in the section. But if you email me or come to my office hours or post it on Piazza, right? Like, I mean, you know, a bit of a flex. I am the most prolific responder on Piazza by me and Will kind of killing it in the Piazza game. So if you post it on Piazza, like I'm refreshing that all the time. So if you have questions other than 5B and then 7 ABC, yeah, post it on Piazza or email me or come to my office hours. Thanks. Cool. So back to the .csv, like the point is like you can open it and it does look very intimidating and like gross, but it is just a bunch of zeros and ones. Like if you opened a like a movie file, like if you took a song on your computer and you like opened it in a text editor, it wouldn't look like this, right? It would just look like zeros and ones. But in this case, it's human readable in the sense that we could scroll through it and we can kind of see like, all right, the first piece of data is like 5, second is 100, third is Arizona State University, and so on and so on. CSV is like nice. And so we use this pandas read underscore CSV function here, and we get an error that says error PD is not defined. Oh, let me screen share back to this. Yeah, so we just say, all right, gif df equals pd.read underscore CSV, foreign gifs universities.csv. And we get name error, PD is not defined. If you see this name error, it's one of the most common pandas, Python errors, right? And it means one of two things. A lot of times it means if the thing in the quotes, like name blank is not defined, if the thing in the blanks is a variable that you're trying to use, that just means like Python has not received a definition for this variable, right? So it's like, I don't know what you're talking about. In this case, it's not a variable though. In this case, it is a short import, right? But the reason we get the error is because if you're just like coding Python and you just start typing like pd.read CSV, you're not gonna be able to load it, right? You have to import it first. So this is just, I just always do this because I want to be able to like show you what generates these errors. But if you do import pandas as PD, like we learned in class this time, right? We say PD and that tells Python like, hey, this isn't a built-in function that I'm using, this is a function. I call a function from that, and then it's read underscore. And then the argument that you give it is like a string, and it is just the file name of the CSV file. It gets tricky because this will work fine in this case where we have this .csv file in the same directory as the notebook that we're working in, right? But if our CSV file, if we want to load a CSV file from a different directory, you have to learn a thing called like file paths. Just the main thing you need to know from file paths is that file paths there are these codes you can use to tell pandas to like look in other directories. So for example, if the CSV file wasn't in this directory, the same directory as the notebook, but it was like one directory above, the code for one directory above in file path language is 2 dots. So if we wanted to say, no, don't load the CSV from this folder, load it from the folder above it in the directory tree, and then a slash, and then foreign gifts underscore universities. So just so you know what's going on with that, if you see like ... slash stuff, the ... just means go up one level. But in this case, our CSV is in the same. And we store it into a variable called gift underscore df, right? Which I just named it that because to remember that it's like gift is the unit, right? Each unit in this data set is a gift given to a university in the US from a foreign entity, and df is data frame. And then the first thing you should do, like reflexively when you load a data set, is that going back to that tidy format thing, it's like we see that each row represents a gift and each column is a property gift amount, right? That's the property of like how much was it, and then country of gift, or that's a property of like what country was it from. Institution name is like what institution was it given to, and so on and so forth. And then like I wanted to know like received the most gifts, right? And so to do that, we would need to do two things, right? First, we would need to scoop the data, and then second, we would need to ask pandas like, what are the most frequent entries in this column, right? And so that's this line of code. And then I'm going over time, but I think after the slide, yeah, the rest is like stuff you're not responsible for knowing. It's just stuff of me showing how you can like do certain cleaning and manipulation of the data set. So like, but it's not like, so I'll just end, I guess the next, I'll end on this slide, yeah. So this slide is just saying, okay, gift df and then these square brackets here. So if you put the name of the data frame and you put the square brackets, it's sort of like the scoop, this known as institution name. So we give it that as a string, we put it inside the square brackets, and then it says, take the whole data frame and just scoop out this column. Right? So then, like if I just did that without the 30,000 things in it, what I do is I say, okay, once you've like scooped that column out, now I want to call this value counts function on it. That tells us it counts the number of times that each value appears, and it tells you like in order, like what's the most frequently appearing thing and how many times, what's the second most frequently appearing value, how frequently, see the top 5 and then also the bottom 5. So the top 5 are universities that receive thousands of gifts: UCLA, Caltech, Johns Hopkins, Columbia, and Ohio State. And then the bottom are colleges that received exactly like one gift, right? Cool, and we see that there's, cool. And then the last thing I want to show you is like, even though it looks really messy, this is just another example of that scooping operator that I talked about, which is like, we take gift df and we start a square bracket, right? And so we're saying we're going to scoop something out of gift df, right? And then if we consider, we can like keep our sanity a little more. If we consider what's inside the square brackets as like a separate thing, like think about it separately, right? Which is like, yeah. So think about what's inside the square brackets separately, and it will like make your life a lot easier, because you'll see that like you can take this thing that I highlighted here and you can just consider it on its own terms, right? It's a command for telling Pandas a thing that we want to scoop out of the data set. In this case, we're going to scoop out the entries where the institution name value is New York University, right? So this is just scooping out. It's going, you can think of it like it's going through each row and it's testing this Boolean operation, right? So it's saying like, okay, go to the first row, see if institution name equals New York University. Go ahead and go to the second row, see if the institution name equals New York University, right? And so on and so forth. And then it just keeps those, right? So like, meaning this does the like checking of whether they're equal to New York University, and then because it's inside the square brackets, that's telling Pandas, okay, now I want you to scoop those records out. Right? So it creates a new data frame, NYUDF. And we can call ahead on that, and we see that it's just, right, it's just the ones with where institution name is New York University. That's all. Yeah.
Jeff, oh, sorry to interrupt you. You know how in like SQL there's like a I-like function?
In what's up? Sorry.
In like SQL there's like a I-like function, right? It's like so instead of like typing out New York University, if you just type in like New York, is there like some sort of function in Python that would like sort of automatically like get whatever is like has New York in it?
I can't really hear you, but here, let me end the main section recording and then